In the previous video, we've discussed the basic introduction to the relativity theory, Michelson-Morley experiment and Einstein's postulates on special theory of relativity. If you didn't watch that video then at first, check it out. The link to that video is given in the I button and in the description box also. We have to know about frame of reference. Generally, a place from where observations are made is called frame of reference. In physics, a frame of reference is represented by a coordinate system with respect to which coordinates of any point in space is determined and is also associated with a clock to measure any event in space. There are two types of frame of reference. One is inertial and another is non-inertial. Two frames are said to be inertial if they are at rest or moving with constant velocity with respect to each other. A frame of reference is said to be non-inertial if it is either accelerating or rotating. Here I said two inertial frames because single absolute inertial frame doesn't exist, whereas single or absolute non-inertial frame exists. You can get many examples of different frames in any standard textbooks. Now let us suppose that an event occurred at a point M, function of x, y, z and t in an inertial frame of reference S. In another inertial frame S', the same event will be specified by four other quantities x', y', z' and t'. Now the S' frame moves along the x-axis with a velocity v with respect to S frame. Since each set of four quantities in S' frame corresponds to the set of four quantities in S frame, the two sets must be related by a relationship. These equations are called the Lorentz transformation. The fact that the speed of light is the same in all reference frames has the consequence that moving clocks run slow. It is called time dilation. Imagine a light clock that consists of two mirrors and a beam of light reflecting back and forth between the mirrors. At first, you are in the same inertial frame as the light clock. You are therefore measuring the proper time, denoted delta t0. The mirrors are separated by distance. The light moves with a speed c. 1 tick is when the light goes from one mirror to the other and back again. The proper time for 1 tick is given by this equation. You are in a different inertial frame to the light clock. The light clock is moving with velocity u meter per second in the x direction. The path the light takes is now different as it has only a finite speed. The time taken for 1 tick is denoted by delta t, the observed time. Now we'll solve an example to understand this effect properly. Muons are elementary particles with a proper lifetime of 2.2 microseconds. They are produced at very high speeds in the upper atmosphere when cosmic rays collide with their molecules. Let the height L0 of the atmosphere be 100 kilometers in the reference frame of the Earth. Now we have to find the minimum speed that enables the muons to survive the journey to the surface of the Earth. The birth and decay of the muon can be considered as the ticks of a clock. In the frame of reference of the Earth, here observer O, this clock is moving, and therefore its ticks are slowed by the time dilation effect. If the muon is moving at a speed that is close to c, the time necessary for it to travel from the top of the atmosphere to the surface of the Earth is delta t equals to L0 by c, is equal to 333 microseconds. The muon is to be observed at the surface of the Earth. It must live for at least 333 microseconds in the Earth's frame of reference. In the muon's frame of reference, the interval between its birth and decay is a proper time interval of 2.2 microseconds. Now by this equation, by solving it we get u equals 0.999978 c. If it were not for the time dilation effect, muons would not survive to reach the Earth's surface. The observation of these muons is a direct verification of the time dilation effect of special relativity. Another important consequence is that a moving object's length is measured to be shorter than its proper length, which is the length as measured in the object's own rest frame. This phenomenon is called length contraction. By similar calculation as time dilation, we can obtain the expression for length contraction. This affects every moving object like a running bus, train, even when you're running. But, under normal circumstances, the effect is so incredibly tiny that it's not noticeable at all. An object needs to be moving at speeds approaching the speed of light before length contraction starts to take a great effect on it. There is another type of time dilation, called gravitational time dilation, which is observed near black holes. But before we discuss it, we have to know about the general theory of relativity. In this figure A, ABCD is a square at rest according to observer ρ, but if it moves with some velocity along x-axis, the length of the arm AB and DC will contract due to length contraction. Now the shape of the square is observed by observer O'P like figure B. Relativity theory is a very complex and important part of physics. It cannot be compressed in one video. But, I think, you are able to understand the next topics if you understand these topics properly. This is basic special relativity theory in a nutshell. There is one more thing, which is very important, as it changed the whole concept of mass and energy. Almost everyone knows about the mass-energy equivalence. Well, you don't know what this is? I think you know the famous equation E=mc². According to this theory, anything having mass has an equivalent amount of energy and vice versa. Mass and energy are related by Einstein's famous formula E=mc², where E is the energy, m is the mass and c is the speed of light in vacuum. We know that speed of light is a very large number, and here the mass multiplied by the speed of light squared. So, this formula implies that even an everyday object at rest with a small amount of mass has a very large amount of energy. Einstein formulated this famous equation, not exactly this formula, in his relativity paper Does the Inertia of an Object Depend upon its Energy Content? In 1905. In the next video, we'll discuss the concept of space-time. Thank you. If you like this video, then please give this video a thumbs up and share it with physics lovers. And, don't forget to subscribe to this channel. Please hit the notification bell icon so that you'll never miss the updates. Join our premium membership for more offers and freebies. Do you know that all the stars, planets, galaxies and other visible objects make up only about 4% of our universe? The other 96% is made of invisible stuff. We cannot see or detect them but know about their existence. This invisible area of the universe is explained in the book The Invisible Creation, written by 𝗁𝗵𝗃𝗃𝗃. This book will give you a transparent idea and knowledge about this deep part of our universe. The subject matter is presented in a simple way, step by step with sufficient illustrations. This book may be of interest to students, teachers, as well as general readers who are interested in astronomy. The book is available in both paperback and Kindle ebook editions at Amazon, Flipkart and Notion Press Store. All the purchase links are given in the description box. Get your copy now.